Hi everyone, welcome. Today's topic is resonance. Okay, today's topic is resonance. We have already discussed about the hyperconjugation and inductive effect. This is resonance. This is also electronic displacement effect like hyperconjugation and inductive effect. Right? Your hyperconjugation, inductive effect and resonance effect. These three effects are very important to understand stability of molecules. Next videos are on stability of molecules. Right? So we are going to discuss about the stability of molecules. So to understand stability of molecules in a very well organized manner, you have to have a good command on resonance effect, inductive effect and hyperconjugation. Okay, so these three effects are very important. Now today's topic is resonance. So first of all, I will discuss about the definition. You don't need to worry. Generally in organic chemistry you have to practice more and more problems, right? So without practicing the questions you can't get very good command on organic chemistry. So if you want to learn theory portion also, right, so learn theory portion through questions. Practice more and more questions in organic chemistry especially. I'm not talking about the physical and inorganic chemistry, but when it comes to organic chemistry you have to practice more and more questions, right? Okay, so first of all, what is resonance? Simple. If you take one structure, okay, if you take some particular structure, you cannot explain the bonding of that particular structure by considering a single Lewis structure of that particular molecule. You have to consider different structures of that molecule. If you take one molecule, you have to consider different structures of that molecule. Then only you can tell about the properties of that particular molecule. That is called resonance. I will explain you very clearly by taking the example. Right? So first of all, to understand this resonance in a very clear manner, I will explain you through examples. I will explain you 5 examples here. You can get a very good command on resonance. Okay, first of all, a simple example I am taking here. C double bond C, single bond C, double bond C. Right? Here H2, H, here H2. Okay, now double single double are in conjugation, so delocalization of electrons takes place, right? Initially if you see here double bond, right, here also double bond, here single bond, but this is not permanent, this is not complete double bond. Why? Because of resonance. If I move these electrons to this position, then these electrons will move to this position, right? After that we will get structure as like this: CH2, single bond C, double bond C, single bond CH2. Now if you observe, initially you have double bond here, now you have single bond, initially you have single bond, now double bond, initially double bond, single bond. That means what is the conclusion? In resonance, double bond can become single bond can become double bond. So there is no complete double bond character, there is no complete single bond character in resonance. Okay, right. Now, for example, I am taking benzene. In the same way, if I take the most popular and successful example of the universe, benzene. So because of the conjugation, here first of all double bond, double bond, double bond. After electron delocalization, I will get this structure, I will get this structure, right? So initially here single bond, now here double bond. So double bond becomes single bond becomes double bond, right? So this is about the resonance. Because of electron delocalization, some double bonds can behave like single bonds can also behave like double bond. So whenever it happens, we can write hybridized structure as like this: bond breaking and bond making. So everywhere there is a double bond character, right? So here double bond, here double bond, here double bond, double bond, double bond. So totally I can write this structure as like this. Okay, next. So first of all, now I am taking one example, a very good example. First of all, I am taking with electron donating group and electron withdrawing group. I will explain you. So 5 cases are there. So first I am taking here, I'm taking here NH2. This is electron donating group, right? First of all, how to write the resonance structure, that is very important. See, here electron donating 1 2 1 2, here lone pair 3 4, this is sp3 hybridized atom. Here 1 2 3 sp2 hybridized atom, right? So this is more electronegative, it will pull electrons towards itself. So what happens? Nitrogen lone pair, and I'm moving this. See, so the moment here, lone pair towards double bond. So the moment here, lone pair to double bond. Remember, and now this is anti-clockwise, this is clockwise. So always, if you once start with anti-clockwise, you have to move anti-clockwise only throughout the process. If you start with clockwise, you have to move clockwise throughout the process. I'm moving anti-clockwise, so this is anti-clockwise. Okay, anti-clockwise. See, now I'm drawing the structures. First of all, first structure is like this, minus double bond NH2 positive, 4 bonds positive. This is the first structure. Again, this is the lone pair double bond. So next movement anti-clockwise, lone pair to double bond. Okay, so this is the next one. Okay, here minus double bond NH2 positive. Okay, again lone pair to double bond, anti-clockwise, moving here, right? Double bond, here minus, here double bond, NH2 positive. Okay, I will give you the conclusion after writing the structures, you don't need to worry. Again, minus to double bond, anti-clockwise. So you have to move anti-clockwise only because we started with anti-clockwise. Here NH2. Dekho. Now this structure and this structure are similar structures. Until you get this similar structure, you have to draw these resonance structures. You have to draw the resonance structures until you get this similar structure. Okay, you take initial molecule like this. So this is the similar structure. See, here double bond, here single bond. In place of this, it is single bond. For suppose I am taking here 1. So first of all, second, third, fourth, fifth bond, sixth bond. So first bond here double bond, here single bond, right? Second bond here single bond. Dekho, right? Second bond here single bond, second bond here double bond. So double bond becomes single bond became double bond, right? So this is the conclusion. Now how many regenerating structures? 1 2 3 4 5, because these are not same structures, these are similar structures. So 1 2 3 4 5. So totally, so conclusion is 5 regenerating structures are there. 5 regenerating structures are there, and double bond becomes single bond become double bond. Next conclusion. Here if you observe, whenever I have the electron donating group, I have electron density at second position. First of all, I have at second position. Next, this is second position, third, fourth. So fourth position, and also at sixth position. Okay, this is the sixth position. So at this sixth position, so the electron density, if you observe, because here I get the minus because of the electron movement. Next at the fourth position, next at the sixth position. So 2 4 6 positions are electron rich. Next, very important thing, what is ortho meta para? Whether when we have electron donating group, this is ortho para directing or meta directing. Dekho, first of all I am taking this, right? So whenever I have the structure like this, if I have any group here, so this is ortho position, these two are ortho positions, these two are meta positions, this is para position. So electron rich positions, this is electron rich position. So okay, this and this are electron rich positions, 2 and 6 positions, right? And fourth position, this is also electron rich position. That means whenever we have the electron donating group, this is ortho para directing group, right? So that means at ortho and para, the positions are electron rich. So whenever we have electron donating group, this is ortho para directing. So these are the conclusions. These are the conclusions. And the hybridized structure, everywhere there is a double bond, so I can write total structure as like this. Total structure as like this. Okay, this is the hybridized structure. So this is how you have to write the resonance structures. Okay, so there is no complete single bond, there is no complete double bond. Next one I am taking now with electron withdrawing group. So what is electron withdrawing group? See, now I am taking the structure as like this. Here COOH. Now 1, 2, 3 sp2, here sp2, but this is electron withdrawing group, so I'm moving this electron towards this and now moving like this. What happens? See, double bond, here positive charge, right, because of this oxygen, here getting positive charge, so the movement is double bond to positive charge atom. So the movement is now clockwise direction. The movement is like this, from the ring it is clockwise direction, so you have to move clockwise direction. So first structure first structure, here double bond O minus OH. Okay, so this is the first structure. Okay, now after moving this, here positive. Okay, so double bond to positive clockwise. Next structure is like this, clockwise, right, clockwise. Here double bond, positive now here COOH, O minus OH, right. Again clockwise, double bond to positive, clockwise, yes. So here double bond, here positive, double bond, CO minus OH, right. Again double bond to positive, clockwise, here double bond, whenever it get positive, this minus came back, COOH, right. Again similar structures, double bond became single bond became double bond. So this is the conclusion. How many resonating structures? 1, 2, 3, 4, 5. So 5 resonating structures. So the first conclusion, 5 resonating structures. Second conclusion, whenever I have electron withdrawing group, electron density more is on first position, third position, and also fifth position, 1, 3, 5. So the electron density is more on 1, 3, 5 positions are electron rich. So whenever 1, 3, 5 positions are electron rich, so here 3, okay, this is 1, this is 3, so 3 and 5 positions are meta positions. 3 and 5 positions are meta positions, we know this. So whenever we have electron withdrawing group is meta directing, so electron donating group orthopara directing, electron withdrawing group meta directing. So 5 resonating structures, and resonance hybrid is like this. Okay, next, so after this I will give you one example. Electron withdrawing group is over, electron donating group is over. You have to practice more and more questions with electron withdrawing group and electron donating group. After this, with electron negative atom, so I am taking this example, cyclopentadienyl anion, right. Now again I am moving this negative charge to this and here, so the moment is negative charged atom to double bond, right, and clockwise. Okay, so the first structure is like this. So until you get this similar structure, you have to rotate. Okay, so now this is double bond, this is minus, this is double bond. This is the first structure, right, clockwise, minus towards double bond, so minus towards double bond minus towards double bond. So I'm getting this structure now. Here double bond, here minus, here double bond, right? Again minus towards double bond, minus towards double bond clockwise, double bond here, minus here, right? Again minus towards double bond. So I'm getting this, here minus, here double bond, here double bond. Again last rotation, minus towards double bond, moving here, then I will get this structure, double bond minus. Dekho, this structure and this structure now same, right? Here there is a double bond, here there is a double bond, here there is a double bond, here there is a double bond. Okay, so this structure and this structure are same, so you have to count only one now. So 1 2 3 4 5, count this or this. So 1 2 3 4 5, so totally 5 resonating structures, here. Okay, and you can observe double bond became single bond became double bond, became single bond became double bond. So that's it. So these are the resonating structures. So this is how you have to write. So another example, tropylium ion or cycloheptatrinyl cation. You will get 7 resonating structures here. So I am taking this here positive charge, right? Now the first movement, double bond to positive, double bond towards positive charged atom clockwise. So this is clockwise. Okay, so you have to rotate throughout clockwise. So first structure, here this is double bond and here get positive. So next one, double bond towards positive, here there is a positive, here double bond. So double bond towards positive clockwise. So move here, move like this, here double bond, positive charge, right? Again double bond towards positive, you will get this structure. Here double bond now, double bond positive, right? Clockwise. Next again clockwise, double bond to positive, double bond to positive, double bond, here double bond positive, right? Again clockwise until you get this similar kind of structure, So I will get this one, double bond, here there is a double bond. Now positive charge is here, again clockwise, again clockwise, here double bond, here positive, here double bond, right? Okay, so this is clockwise. Again I am moving this bond here clockwise, double bond positive. Dekho, so this structure and this structure is same, so count 1. So 1 2 3 4 5 6 7, so total 7 resonating structures, So this is how you have to write resonating structures. Only concentrate on this first structure. So you are moving from where to where and how you are moving, clockwise or anti-clockwise. Okay, if you start with clockwise direction, then you have to continue with the clockwise direction only. If you start with anti-clockwise, you have to continue with anti-clockwise throughout the process, right? Okay, so after this, when we have the radical, electron withdrawing group is over, donating group is over, positive charged atom, negative charged atom over. Now if I have like this, for suppose single bond C, if I have the radical like this, right, instead of positive charge I have the radical. Now what happens? Whenever I have the radical here, homolytic cleavage. So whenever homolytic cleavage takes place, now radical is here, CH, and here double bond, 1 2 3 4. Now this is CH2, right? So initially radical is here, now radical is here, so I can write the total structure, hybridized structure is like this, right? Hybridized structure is like this. Okay, this is partial double bond, right? Here radical, here radical. So this is hybridized structure. Okay, so after this, important thing, whenever I have open chain, not cyclic system, whenever I have the open chain and only one direction and open chain, how can you calculate number of regenerating structures? So every time we cannot draw regenerating structures. So this is the simple trick. When we have open chain, with single direction, number of resonating structures, which is equal to double bond, number of double bond participated, double bonds participated in resonance, number of double bonds participated plus 1. For suppose, for example, I am giving here double bond, here positive charge. So only one direction, double bond is moving towards positive, one direction, and also it is open system. So whenever we have system like this, number of regenerating structures without drawing, here double bond, pi bond, 1. This is participating here, so 1 plus 1, so total 2. So if you see, total 2 regenerating structures. This is one regenerating structure. If you move this double bond towards here, another regenerating structure, only 2 regenerating structures possible. So 2 regenerating structures. Second trick. So what is the second trick? If you have non-benzenoid compounds, if you have cyclic non-benzenoid, means without benzene ring, non-benzenoid compounds, whenever we have non-benzenoid, you have to see the corners are the total atoms. For suppose I have this structure, right, furan structure. So how many regenerating structures? This is first of all cyclic and this is non-benzenoid, there is no benzene ring. So 1 total atoms, 1 2 3 4 5. So totally you will get 5 regenerating structures. If you have this cyclopropenyl cation, again cycloheptatrienal cation, okay, cycloheptatrienal cation. So totally this is cyclic and non-benzenoid. So 1 2 3 4 5 6 7. So totally 7 regenerating structures. If you have this cyclopentadienyl anion, this is also cyclic and non-benzenoid, totally 5 atoms, 5 carbon atoms, so 5 regenerating structures. Okay, so this is how you have to write regenerating structures and number of regenerating structures. So this is, I have to complete this total resonance in the next video. So after that we will go with the stability of the molecules. Stability of the molecules are very important, right? So you know, inductive effect, hyperconjugation, resonance effect. In these 3, mesomeric resonance effect is nothing but mesomeric effect. So mesomeric effect always dominates in stability, right? So I will discuss about these all things again in my lateral classes. Okay, so thank you so much for watching. Have a nice day.